I'm Kevin, and I'm going to be talking about static analysis and how you can use it to find vulnerabilities. So let me start off in saying a little bit about my background. I started off as a security consultant, looking at web application after web application, looking for vulnerabilities. And within 6 months of that, I began to look like this. Whenever I was put on a new gig, I would just kind of do the same boring, repetitive task. And after a while, I began to look at computers for a way to automate this like mundane process. So I turned to static analysis. And what is static analysis? It's automated code review. It's learning about your code without actually running it. And so let's start with one problem called SSRF. It stands for server-side request forgery that I typically found as a security consultant. It happens when you can send a URL to an application, and that application sends a request to that URL for you. Now, that might not seem so bad, but it is for typically one reason. Networks can be like Pop-Tarts. They're hard on the outside and only allow HTTP in through the firewall. And they're soft and gooey on the inside. And so once you're past the firewall, you can access Elasticsearch, Kibana, the AWS metadata service, et cetera, et cetera. And there have been a lot of public instances of this turned into remote code execution. So for a code example of how you might have this in your application, say you have a user who can upload their photo to your website. You can take the image name from the request, and we'll call that a source. And it might flow into a dangerous function like URL open, which is what sends the URL the request. And this process of seeing if something from a source can flow into something called a sink is called taint tracking. And there might be some things that get in the way that make your vulnerability not possible or exploitable. In this case, there's an image name .ends with that could be fooled by the fragment identifier trick, like the hashtag at the end of a URL that's typically ignored, not sent to the server. So in this case, we would see that image name flows into URL open and then report it as a vulnerability. So what if we could solve all similar problems? Wouldn't that be great? We could focus on kind of finding vulnerabilities that aren't the same kind of pattern of source to sink. And so what makes for great static analysis? It's accurate, so it doesn't waste your time with a bunch of false positives, and you can't really trust the alerts that you get most of the time. It's insightful, so it finds things that, say, grep wouldn't be able to find. And it's parallelizable, so it scales to millions of lines of like Instagram's code base and whatever. And it's flexible, so you can ask it things that you didn't think to ask before. So if you have limited amount of time and it's just like an open source side project, you'd probably pick the first two. And so introducing PyT, it's a static analysis tool for finding these kinds of vulnerabilities in web applications. And there's a lot of pieces to it, like this 8 folders inside the main folder. Let's start with the CFG folder. CFG stands for control flow graph, and it's basically a graph of the possible execution paths through your program. On the left, we have the familiar else, if else. On the right, we have a loop. And so the nodes of the control flow graph are called basic blocks. And once we have a control flow graph, we can do what is called data flow analysis. And data flow analysis is similar to control flow analysis, but instead of the possible execution paths, it's how variables flow through your program. And so how we do data flow analysis is there's typically 2 formulas for each basic block inside the control flow graph. And there's one for in and one for out. And in PyT, we use something called reaching definitions, or a modified version of it, rather, so that we can go from source and see that the source reaches the dangerous sinks. And so the inset, the first half of it, is pretty easy. It's just the union of the reaching out set of the preceding basic blocks. And so like there's a lot of formal notation with program analysis, but like it's easier to just walk through an example. So here in our first basic block, we have the first definition, x equals 5. And so there's no preceding basic blocks. So the inset is empty, and the outset is D1. The next basic block doesn't have any assignments. And so the inset just equals the outset. Then the last basic block, definition 2 kills definition 1. And so the outset is just D2. Whereas the inset on the first iteration is D1, and on the subsequent iterations will be D2, so the inset is both. And so reaching definitions tells us that a source reaches a sink, but it doesn't tell us how, which can be important for false positive reduction. And so we use something called a def use chain, which is just a succinct way of saying a dictionary with definitions mapped to their uses. And so for an example, say we have this source location. It flows into the URL for function, which can only really return previously defined URLs inside your application. So we don't really care that much about the return value of URL for a security reason. Whereas if location flows into os.path.join, location can do ... / whatever. And so os.path.join more or less returns location. So we care about directory. And so when both of these flow into subprocess.call, then the directory will be a vulnerability, whereas the other variable won't. And so I sort of skipped over that part where I said, once we have a CFG, how do we make the CFG? There's no import CFG, cfg.rpython file, but there is import AST, which CPython uses when it looks at your Python code before it, like emits bytecode based on this. And so it's an abstract syntax tree is a tree representation of the abstract syntactic context of your program. So here on the left we have an assignment, a for loop, and a print call. And here on the right in the abstract syntax tree we have an assignment with target and value, name, numbers, etc. And so once we have this abstract syntax tree, we can use what's called the visitor pattern and just visit all of these different nodes inside the tree. And all the different nodes inside the tree are based on the abstract grammar of Python. So see like assignments has targets and a value, et cetera, et cetera. And so once we have enough of these visit underscore whatever functions in our statement expression visitor classes, we can just have visit underscore foo, visit underscore bar, like if, else, for, etc. And so once you handle all these different kind of nodes inside the abstract grammar, you can pretty much scale to like pretty complex programs because there's a pretty finite amount of nodes and infinite amount of lines, more or less. And so how effective is this, source to sink and def use and et cetera, et cetera? So I looked for open redirects in a bunch of like open source Flask projects. What's an open redirect? It's not a very exciting bug class. You say send your grandma chase.com, and chase.com takes a next parameter, and chase.com doesn't, whitelist your next parameter, and so, they get sent to evil.com where they fish your grandma's, username and password. And so there was a CSV file of like 481 open source repos. At first, I wanted to see, where the vulnerabilities actually were, so I can compare, the true results with the output of the tool. And so I ran 2 regular expressions on the code. One to just see redirect calls with a variable inside, and then the next with redirect with request.whatever inside. And so that narrowed it down to 20 repos that I could just run the tool on and kind of compare the true positives with the reported results. Out of the 20 repos, 4 4 out of 6 true positives were reported. We had this evaluation was ran in last November, so like there were certain expressions we weren't handling. And there were 5 repos that had a false positive, mostly due to us not having a good mapping of between like the URL for os.path.join type stuff. So now it does 5 out of 6. I have an open PR for handling all the expressions. And then 2 repos still have constraints that we really can't solve, like regular expressions, for instance, unless you have a string solver that you can kind of pass all those constraints to, and it tell you whether or not, or for a particular sync, that those constraints, make it, not exploitable. Those are kind of just, as best as we can do. So there's some other awesome open source tools, like PyBay came out earlier this year. Right now it's a static type checker, and I guess like soon it will be a vulnerability finding tool. It's written in OCaml, it scales to millions of lines. They've done a lot of great work with PHP that's, I think, closed sourced right now, but like they're definitely doing some great work in this space. Bandit was originally made by OpenStack. It unfortunately doesn't do data flow analysis, so you do get a lot of false positives, but it was kind of the first and foremost tool that inspired all the others. And then Uber, like a couple of years ago, released, so it basically did reaching definitions, but backwards. That's called backward slicing, and so they both kind of do exactly the same thing. And then these are just some additional resources you might be interested in, like lgtm.com is free for open source repos, and so they have a lot of great program analysis stuff, and they do have the flexible queries that you just, it's kind of like SQL in that you can just ask it whatever you want, similar to like OS query or something like that. And so yeah, that's pretty much the end of my talk. And if you'd like to talk to me afterwards, I'm definitely open to that. But does anyone have any questions?
Thank you, Kevin. Anyone have questions? We're taking questions.
Thanks. Can you mention how long it takes to run static analysis on some of the open source code bases that you ran on?
Yeah, that's a good question. It widely varies between how big the code base is. For like microservices in your, in your company's code base are probably not going to be an issue, and it's just going to take, maybe 2 or 3 minutes. Whereas like monolithic code bases, like a lot of companies have just millions of lines of code and stuff. So there's 2 ways of doing like one function calls another function. One way of doing that is inlining, where you kind of just like copy and paste the function that you're calling into the function that's calling it. And so that you kind of redo a lot of the same work, because the same function can be called 5 times in 5 different places. And that's what PyT currently does. Whereas like PyBay, I think, does inlining, so it has summaries of functions, so it like doesn't do as much of the same work. It can just all be in parallel. And so PyBay is probably a lot faster than PyT. I haven't like done it side by side yet. But yeah, it should just take a few minutes if it's not like a huge monolithic code base. Yeah.
So in a CI context, is there a mechanism for like handling false positives when they're marked as such?
Yeah. So the question, just to repeat it, was in a CI context, is there any way to like mark false positives and kind of don't report off of the same vulnerabilities over and over again? Yeah, so there's a few tools that have, so Bandit and Detect Secrets from Yelp and PyT all have what's called a baseline. And so the baseline is just a file of previous runs of JSON output. And so like it just takes in the previous run and doesn't report anything different. You can also add like like the comment no sec at the end of your line, and that's another way to whitelist things. We don't yet have like an audit functionality that you can just like give it a baseline, then hit yes or no, yes or no. But if it's in the baseline and you pass a baseline, then it won't report on the same things over and over again, which is important because, yeah, like you mentioned.
For a team that's developing a new service and is running this analysis daily, how does this affect their development or affect the design? What new patterns do you see?
That's a good question. Like, I've used it a bit in that, like, there's oftentimes, even with something like Bandit, whereas if your security team has a secure replacement of a vulnerable function, like say advocate can replace request from Kenneth Wrights, in that it's not vulnerable to SSRF. And so a lot of, if you use it a lot and it keeps on reporting, you know, request dot whatever, you'll probably just use advocate instead of that so that you don't get the same, like, as long as you have a secure wrapper, you don't even need to do any data flow analysis. You can just alert off of the bad request dot whatever or URL for it, etc. I mean URL open. So yeah, I guess just to recap, like, you know, not using the same vulnerable functions, using a secure alternative that you wrote yourself. Cool. Well, thank you, everyone.
Thank you, Kevin. Let's give Kevin a hand one more time.